Hello everyone, today I'll talk about the solution to the problem spiral matrix 4. We're given a linked list, we have to copy the numbers from the linked list into an array in a spiral pattern, and if there is any spaces left we have to fill them with -1s. So this is not really a linked list problem, the only thing that we'll use our linked list for is to iterate through it, and it's really a spiral matrix problem. So how do we approach a problem about spiral matrices? So there are two main ways of traversing a spiral matrix, or at least two ways that I tend to use. One way which we can use in this problem is that since we'll be filling the values first here, in that direction, then downwards, and so on, then we can just turn, because of course we'll have to implement turning, and implementing turning is very simple. We'll be having traditional directions, the same way that we have on the grid, in the proper order. So first we increase columns, then increase rows, then decrease columns, then decrease rows. That's this turning clockwise. So we have those directions which we'll be using. And remember the direction we're heading to currently. And after every turning step, which we have to determine somehow, we have to increment our direction and we have to modulo it with 4, which in this case is implemented as ending with 3, which I'll talk about later. So we essentially have to keep turning clockwise, and in this problem, since we're building this matrix, we can do it by but just looking at if we have reached an edge, while an edge is both when we go outside of the matrix, that would be an edge, but also if we see a cell that we've painted over already. So here we have been turning by reaching the end of the matrix. Now here we go upwards, and we turn because we've reached this painted cell already. So that is one way of doing it. Another way of doing it is just to notice how many steps you have to take whenever you go the next row or column in our spiral order. So for instance, you can see that here at the first step you have to go whole with steps. Now, since this cell is already painted, here you have height -1 steps. Since this cell is painted, you have width -1 steps. This cell is painted, so you have height -2 steps because this cell is also painted. So we can see what happens here. First we go with steps and decrement height. Then we go the current height, number of steps, which is h-1, we decrement width. Go with, decrement height, and so on. And of course, whenever we have nothing to do, we just turn but do not write anything. And this is what I'm implementing here. This has also the benefit that it works when you don't have some markers within the matrix that you can tell that you have already visited the given slot, but it on the other hand requires that you know the dimensions of the matrix at the beginning. So we just have to go through our linked list. And in this case, we'll be filling our result with values from this linked list that we're given as head. We'll just be pushing the head forward, taking its value and pushing it forward whenever we write into the matrix. Whenever we have no more values, we just break. And the matrix is initialized with -1s at the beginning. One weird trick that we can do here is instead of taking our linked list and then padding with -1s, we could add another node. So if we have a linked list, something's happening here, and this is the end, then we could point it to -1 and point that -1 to itself. And in that case, we have an infinite linked list that has all the values of the original linked list, and then an infinite amount of -1s, right? -1. So this would be one way, and then we do not have to check if head, and we only have to check if we have run out of the matrix. However, in that case, we have to always go through all the fields, and in this case we have the opportunity to exit early if the linked list is small compared to the number of slots in our matrix. So both of those approaches have some benefits and some negatives. So we start, of course, we want to start at painting 0, 0, since the way I'm implementing here is that we first take a step. So we determine the direction. First we take the step, then we paint over the position, then we start at position 0, minus 1. So the position to the left of the first one. That's because we want the first step to go to 0, 0. There are other ways of implementing it, because this is just an implementation issue. And of course we do it for the appropriate number of steps, which we had in this case, with height minus 1, width minus 1, and so on, which will be calculated here on line 15. I mentioned this here, that ending with 3 is the same thing as modulo 4. That's because when you have a number in binary form, then what is a remainder from division by 4? Well, we know that 4 in binary is just 1, 0, 0. And 3 in binary is thus just 1, 1. And that means that a number written in binary is this part is essentially this value multiplied by 4, and then this value is added to it, and this value is always less than 4 because it does not have a 1 here. So we can see by just looking at the binary representation of a number, the part that is the result of division by 4, because division by 4 is just shifting 2 places to the right, which would be just forgetting this part, right? That would be division by 4. And so the remainder is everything else that remains. After we shift to the right and then shift to the left, this part is the remainder. And to get this part, so to get only the last 2 bits, we can just binary end it with something that has only those 2 bits set, which is a 3. Because it has here leading zeros all the way, so everything here after the end will be equal to 0. So that is one weird tricky way of, well, it's not really tricky, but it's not really readable if you don't typically use binary bitwise operations to write modulo 4. But of course, it's also in a way nice, because modulo is typically an expensive operation, and probably most modern languages will always optimize. Well, modulo by power of 2 is very easy to optimize. Most languages optimize modulo by any value that is known at runtime, because then by some magic of number theory it can be changed into multiplication. But in this case it's also possible to write it out explicitly. It's that easy. And now this line 15, I've intentionally made it pretty maybe difficult to understand. So feel free to pause the video and try to puzzle over what's going on here. How does it implement this weird situation that we've had here? Because really this really shows why I don't like multi-line assignments where something exists both on the left and on the right. Maybe except for the most basic form, which is AB equal to BA, which is the idiomatic way to swap 2 values in Python. And that's as far as I'm willing to go with values appearing on both the left and right side. But because there are some weird operations, order of operations that happen here, and essentially what we want to get here is we want to calculate the steps. We want to swap m and n with each other and decrement one of them. So at first our steps will have to be n, which is the width in this case, and then we want to swap n and m, so nm becomes equal to mn. However, this second one should be decremented. So not the one that we're taking as steps, but m should be decremented. So steps becomes, at the same time, steps becomes n becomes m minus 1, and m becomes n. And really, it would be much clearer if we write it out as fors, or as ifs and elses, but I decided to leave that one in because it really showcases why it's pretty difficult sometimes to understand multi-line assignments, and that they hide some pretty tough control flow at some points. And at the end, of course, we return the result, and we run until we either run out of the values in our linked list, in which case we know that the negative ones are already filled in all the other spots, or we run out of either the width or height, because in that case there is nothing else to write in, everything has been written.